This is the last section in Chapter 4, a discussion on uniform circular motion. What we have in this case is we have an object that is confined to move around a circle of radius r, and this object is moving around the circle in such a way that it has a velocity that is constantly pointing out of the circle. We call that the tangential velocity, vt. And then we have a center-seeking acceleration that is called the centripetal acceleration. And as we move around the circle, the centripetal acceleration is always pointing towards the center. Now you have to think about that carefully. In this position right here, in the first circle, you see the velocity is pointing up, the tangential velocity is pointing up, and the center-seeking acceleration is pointing in. We assume that the object is moving in a counterclockwise direction at this point. So sometime later, we're going to have a situation where we're still in the circle. Again, I apologize about my drawing. And now we're at the top of the circle. The tangential velocity, vt, is pointing to the left, and the centripetal acceleration is still pointing toward the center. And again, that centripetal acceleration represents a center-seeking acceleration. It keeps us in what's called uniform circular motion. That's what we're talking about here. We can calculate the centripetal acceleration from a very simple equation, and that equation is that the centripetal acceleration, A sub c, is equal to tangential velocity squared divided by the radius of my circle. The centripetal acceleration is equal to the tangential velocity squared over r, or just vt squared over r. Now another equation that comes up fairly often is the period of the motion. The period of the motion represents the time that it takes to complete one revolution around this circle when you are traveling in uniform circular motion. Again, the term uniform here is the key. It's assumed that you're not speeding up or slowing down. Think about the rotation around a clock. It takes 60 seconds to rotate around the clock if you're on the second hand, correct? The period is given by the equation t, which represents the period, is equal to the distance traveled around a circle, which would be the circumference of a circle, 2 pi times the radius, divided by the velocity tangential. So 2 pi r over v sub t gives you the period of your uniform circular motion. Now let's just do a simple example to make sure that we understand what's going on here. We can properly use these equations. Let's say that the radius of our circle, if we're moving in uniform circular motion, is equal to 5 meters, and the tangential velocity is equal to 10 meters per second. Now note that in this example I'm using meters per second for the tangential velocity, and I'm giving the radius in meters. If we wanted to calculate the centripetal acceleration, that would be equal to vt squared over r, tangential velocity over the radius. In this case, we have 10 squared divided by the radius 5, or just 100 divided by 5, and so the centripetal acceleration is equal to 20. And if you check your units, in the numerator, you're going to have meters squared per second squared because you're squaring meters per second. In the denominator, you have meters, so as we expect, we get meters per second squared. So the units check out. Once again, the tangential velocity is 10 meters per second. We square that, so we have 100 over the radius 5. 100 over 5 is 20 meters per second squared. And finally on this example, if we wanted to figure out the period, we set the period equation. T is equal to 2 pi r over v sub t. Using our variables in this equation, we have 2 pi multiplied by the radius, which is 5, and then divided by the tangential velocity 10, or we just have that the period is equal to pi seconds. So 3.14159 seconds. Notice that the units on this, once again, are seconds because we have meters in the top in the numerator. We have meters per second in the denominator, so the meters cancel out, the seconds come up top, and we have a period given in seconds.